you
in front of me. No, just stand in front of me. Put it back in your chest. Don't be so good. Now face me. Face me. Hello, welcome to the first Onward essays session of this year's Splash. This is the 10th anniversary of the essays stuff at Oopsla/Splash. Today we're going to have two presentations, and we're going to just jump right into it because we're here to hear them and not anyone else. My name is Richard Gabriel, and the first talk is of type preposition, determiner, adjective, noun, preposition, noun by Tomas Petricek.
Thank you. Now we can argue about the meaning of types. So thanks for coming. And I'm not going to tell you what's the title of my talk, but here I just call it History and Philosophy of Types because that's the sort of part of the essay that I'm going to be talking about. There's more in the essay, so if you I guess this is just the advertisement for the essay, really. Now what I want to talk about here is partly inspired by this question, what is a type? Many people here, probably everyone, has done something with some types in programming at some point, and I've done a lot of stuff with types as well, and I still don't know what it is. So that was one of the questions that sort of attracted me to the topic. There was also an essay last year at Onward trying to understand some of the structure behind types, so distinguishing between the logical notion of types, which is sort of one way of thinking about types, and the more engineering aspect of it. And that sort of was a nice introduction that you can actually trace and look at different backgrounds. And what I'm going to try to do here is to, in a way, go even further along this quote, which says, "Science is much more sloppy and irrational than its methodological image." So when people talk about types, that's one place where you can nicely see this because we are all scientists and we should be building this perfect image of nature or finding the truth, but whenever you hear two scientists talking about types, you see that there's a lot of irrationality, there's a lot of disagreements, they don't even have a common definition. And what I'm going to do here is that I'm not going to try to find the universal common definition, but instead I'll actually try to explain some of the aspects behind why is it that we just can't find it, and why is it a good thing. So when I was trying to understand what is a type, I went to the lecture notes for the types lecture at Cambridge, where it says, it doesn't really give you a definition, but in the introduction they tell you what are types good for, why are we using them. And it has this nice list where types are good for detecting errors via type checking, they support abstraction, they let you document your code better, or they serve as a documentation, you can use them for efficiency, and they give you whole language safety. And whenever I was supervising this course, I asked my students and they nicely recited the list. And then whenever you look at any of the programming languages today that have types, they might be still using some of those, but it's really rare that one programming language would have types with all these properties. So one interesting example is languages like Dart and TypeScript, which end up, so they are not type sound, so that's the 5-point out. They also just compile to JavaScript. They erase all the types, so that's 4 out as well. and they do exist for the abstraction and the documentation. But then there's other kinds of languages with types, say some of the dependently typed languages like Coq, where people actually sort of, they don't even write programs with them, or some of them do, but some of them don't. But they can use them for rebuilding the foundations of mathematics, and yeah, what's whole language safety there? So I think it's really interesting to see that if you have this nice list here, it might work for ML, which is probably when the lecture notes were first created. And contrast this with what people are doing what other things are people doing with types, and how they're just breaking all of these nice good things that we get from types. So what I want to talk about mainly two things. The first half, I'll just go through some of the history of types, of the concept, and in the second part, I'll talk more about the philosophy aspect. So this is going to be a quick overview, which I sort of need for the later part, where I'm going to try to explain some of the developments using fairly standard ideas from philosophy of science. Do we have any philosophers of science in the audience? Very good. So you can then correct me. Now on the history side, so I think the first use of types that people refer to when they talk about types in programming is from Bertrand Russell, from his paper, or a book in 1908, back then it was a paper, where he had this problem in set theory with paradoxes of the kind class of all classes that do not contain themselves as elements. So when I say I am lying, that's the example. And it's this sort of self-referential nature that's making this all go wrong. And so what Russell did is that he introduced types, and he says base formulas have type 0, and formula that uses a formula of type n will have a type n plus 1. So when I say I am lying, when I say I am lying, the I in this I am lying refers to something of a different. This is always confusing. So when I say I am lying, that is a theorem of a different type than the theorem that's appearing in this statement. So I'm trying to refer within something of type n plus 1 to something of type n. And one interesting thing that's happening here is that he isn't saying this is malformed program or statement and we should rule it out. He will still let you say I am lying. He's just saying when you say I am lying, you're not actually referring to the thing you're saying. So you're referring to something of a lower type in something of a higher type, and so it's not actually saying I am lying about this theorem that I'm saying. But now I just made it very confusing. But that's all right. The important bit here is how does he actually work with the types? What does he do with it? And the confusing thing I was trying to explain is that he just labels things with types but doesn't use them to rule out invalid things, which is really one important difference from, say, programming languages that use static types to rule out invalid programs. The other interesting thing here is that Bertrand Russell actually says it's unnecessary to know what objects belong to the lowest type. In practice, only the relative types are relevant. So you don't need to know what is a type specifically. Like you don't have to interpret it as anything concrete. You just care about the relative structure. And we as programmers really care about the specific types as well. Like, it's really important to know that something is int, something is string, and what that means. And I think for me, one really important bit there is that he never says you should think of types as sets of values. And in programming, treating types as sets of values is probably the most common way of thinking. So a lot of the type theory, a lot of the work on type systems basically builds along the idea that types are sets. And this is something that when types were first created wasn't there. So types were not sets of values. The second sort of appearance of types, and I'm not doing a full complete history, I'm not a historian, I just picked a few elements to illustrate this. So in Alonzo Church's work on simply typed lambda calculus, that's another piece of work that we now see as the sort of foundation of functional programming. But when he was doing it, he wasn't thinking of foundations of functional programming because that didn't exist. Programming didn't exist. So the work was really looking at foundations of mathematics. And again, he had these types in the system which are formally surprisingly similar to types in functional programming. But again, he says, well, it doesn't really matter what are the types at the lowest level. We just need to track the relative nature. And the formal theory admits a variety of interpretations. So he was sort of building some formal system where he had types, but again, it wasn't sets of values, or it wasn't really relevant what the meaning of the types there is. Now I skipped Algol, where types sort of came from what Stephen in the last year's talks calls the engineering tradition. And I'm going to jump a bit later where they figured out how they can talk, what are the types in languages like Algol, how can we deal with them? And so Tony Hoare is sort of the first person, as far as I know, who really says that types, you can think of them as sets of values. Which was sort of building on some previous work. And this is really important idea that I think is behind a lot of the programming language theory work. So just this step sort of allowed people later on to do things like the standard in type theory when you prove soundness. You're using the progress and preservation theorems. That's all fundamentally based on this idea that we're working on sets, because you're saying the value that the program is going to produce belongs to the set denoted by the type. So this is probably the most prevalent view of how programmers think about types. There are some curious things that don't really fit with the model very well. Like when you look at pointers, what does that mean? Well, suddenly pointer is just you can say, well, it's just a number that represents the memory of the address in the memory of the machine, but then you're just losing all this nice mathematical abstraction around it. So it's a nice idea that works surprisingly well for many things. It still has some holes in it. Another interesting area where I think this idea of types as sets fails is when we look even more towards recent developments, and we look at programming languages with effect systems. So here, it's like an ML-style assignment where I'm reading the value of S and modifying the value of the R. And the type you can give to this in languages with effect systems is, well, assuming R and S are some memory cells or references in regions rho and sigma. The type of this is that it produces nothing. It's just a unit. It doesn't give me any value. But it writes into the memory region rho and reads from a memory region sigma. So this is another type system, another kind of type system that people are building. And again, this is where the sort of idea with sets doesn't really work, because what kind of set is this type unit which also modifies or accesses some memory regions? And so you can come up with models, like you can say, well, actually, my types are functions from world to world with the result, but then it's just becoming really, really complicated. And it's not, you're losing this nice intuition. So there's more recent work that's trying to take a different approach, and instead of treating types as sets, you can actually treat them as some sort of relations, where we are saying the relation that models this is relation between the old world and the new world, where everything stays the same except for the region rho, and no changes in the region sigma, no changes anywhere except for the region sigma will have effect. So there's more work happening on types where people are coming up with different models based on other work that's happening around types. And I think if we look at some of the sort of programming languages that people are working with currently, it's getting even more complicated, because there are languages that actually ignore this soundness idea, like Dart and TypeScript that I mentioned before, and they're just using types for other good things that we figured out we can do with types, like editors, documentation tools, and so on. There's languages that are actually just focusing on making the correctness even stricter. So in say, Agda or Idris, we can prove more things about our programs, and the types tell us even more to the extent that the IDS will be able to formally verify everything. Another interesting direction is with F# and type providers, because in F# you can actually, F# is ML based, so it has the very strong ML-like static type systems, but you can import types from external sort of data sources. So suddenly a country like Czech Republic or United States can become a type in your type system. And that's, again, breaking some of the core assumptions, because your program will type check as long as the country exists. So in science, we'd like to have this nice idea that we are getting closer to the truth, the right definition, and I think many of the examples of what people are doing with types show that, well, it's not like we're getting closer. There's just a lot of really complicated developments that go in all sorts of directions. Everybody's using types for different things. They have different core assumptions about what you need, what you expect from your types, and when two people like this come into one room, they'll end up fighting, and so on. Unless it happens on the internet, of course. So, yeah, with virtual reality, maybe. So, I guess the picture I tried to show with the previous part was this idea that things are really very complicated. There's a lot of disagreements, a lot of mismatch, and there's no order. But I think there is a lot of interesting work in philosophy of science, where philosophers of science have looked at the history, and they tried to find some of the structure in how science actually worked. And some of these ideas, I think, are really interesting when we talk about types as well. I'll actually start with the most chaotic one, or with the least structured. So should there be one clear definition of types? And this is a nice quote from Paul Feyerabend, who says, "To clarify the terms does not mean to study the additional properties of the domain in question. It means to fill them with existing notions from an entirely different domain of logic." And that's something that I think people in programming languages world often do when someone comes up with a new weird definition of type, and we ask them, well, give us a precise definition, be clear. What they sort of have to do is to actually say, well, I don't know, it's really complicated. I'm not, this is like early idea, and I don't really have clear definition. That's something they could do, but if we sort of insist on the clarity in the early days, we often end up just taking the existing concepts where we already have the clarity and trying to take that different idea and reduce it to what we understand. So this is one thing that, according to Paul Feyerabend, is often happening in science, and he's sort of fighting against it. So if we have something that's really weird and kind of different, it doesn't really make sense, we shouldn't try to clarify it using our current idea of what clear means. And he says, well, later on, when that idea is fully developed and there's larger community around it, we might actually come up with a different logic for it that will let us be clear. But it doesn't really work with this sort of early ideas. So that was a bit sort of trying to influence how we work with types when we start doing something weird and crazy. The other part is trying to understand some of the structure. And one really nice theory that I think fits extremely well for the use in programming languages is Lakatos' idea of research programs, where he says, well, science consists of multiple competing, potentially inconsistent research programs. So you have these different groups of people who have some who are part of one research programs, they understand each other, but they might actually be, what they believe in might be inconsistent with what other people believe in. And the research programs consists of hardcore, which is the core assumptions that you're never willing to violate. So that could be, it could be your idea that type systems have to be sound. Like that's your hardcore. And then you have auxiliary assumptions, which is sort of all the things where research happens, where we are allowed to fiddle with things. So if I'm a strict type system person, I'll tell you, yes, type systems have to be sound. They have to have the soundness proof. But then you can invent type systems for checking different parts of programs and so on. And the core assumptions are not to be blamed for any apparent failure. So if you say, what would be a good example? Well, if I'm building a type system that has to be, if I believe that type system has to be this automated mechanism that has to work without human intervention, so it's just type checking. If I believe that program with types, there should be a decidable type checking procedure, then I'm not going to make my types undecidable. That would be breaking the core assumption. I'll just keep adding things in different areas and say, well, the fact that you can't check this program means that your type system isn't good enough, but that could be fixed. We could just make it more complicated in this one direction. You're never going to admit that actually maybe your core assumption is what's the problem there. So you're building in this auxiliary assumptions, and of course, whenever you meet someone who believes in different sets of core assumptions, you will not really be able to talk with them. Another interesting bit that I think also fits really well, and is also from Imre Lakatos, is the idea of concept stretching. So this is what happens when someone comes up with a new counterexample that was of a kind or of a structure that nobody realized before. Now, he actually talks about this in concept of philosophy of mathematics, and he talks about the Eulerian formula for polyhedra, where there's some relationship between the number of faces, edges, and vertices if you look at polyhedra. And then in sort of when it was first discovered, it was, you'll have to Google it yourself, but it's like vertices minus edges plus faces is 2. And that works until someone comes up with a polyhedra that has a tunnel through it, because then it's 4. And how people react to this is that, well, someone comes with a counterexample, and they suddenly extend this idea of polyhedron from all these nice polyhedra without any holes in them, and says, well, actually, if you have a hole through it, it's still a polyhedra. And it sort of matches the definition, but it's an example that nobody ever found reasonable. So they're extending, they're stretching the concept by adding something that kind of fits there, but only once you actually see it. And the weird thing is, we do not really see that the concept has been stretched, because it's still a polyhedra. Yeah, this is a valid example, but once you see it, you're in this weird state where your theorems no longer works because someone gave you a weird counterexample, but you still don't feel that's correct. And he has a beautiful example, which is a letter from Charles Hermit, who says, I turn aside with a shudder of horror from this lamentable plague of functions which have no derivative. So this is the typical reaction of someone who's faced with the concept stretching happening. And of course, I did a few replacements here. It's not actual quote from the Hacker News website, because people these days don't write that nice critics. But if you search the internet for anything that people said about Dart and TypeScript's type system, you will see this sort of behavior where they kind of feel that it's still a type, so they feel really strongly about it. But because it's breaking one of those core assumptions, it's extending the world of what is a type, they feel really, really bad about it. And I think that the Dart and TypeScript and their lack of soundness is a really nice example of that. So the next question that sort of philosophy of science sometimes tries to find or answer is, what's the right scientific method? How do we proceed to accumulate knowledge and tell more about the world? And there's a lot of, this is actually a really interesting problem, I think, for computer science, because the discipline doesn't really quite match fields like physics, where a lot of the philosophy of science has been done. And so I'm not really sure what's the sort of similar work in philosophy of science that would actually be directly relevant to computer science. But one interesting point that was made by Paul Feyerabend is, if you look at the rich material provided by the history, it will become clear that there's only one principle that can be defended under all circumstances, and that's anything goes. Now, he actually doesn't mean by this that there's no method. He doesn't say you should be free to do whatever. What he's saying is that if you there's no unifying principle that would actually sort of unify everything that happened in the past. And there might be principles, and there usually are principles that worked for some period of time in some communities. So if you have some way of building programming languages together with their mathematical models, that might give you a really nice method to continue building and build more interesting things. But it doesn't mean that that's the only right way to go. The anything goes means there might be another method that will actually let you do other interesting things. And I think this is again one point that we in the computer science world often sort of don't realize or ignore or try to ignore, where we tend to follow one method that's been used previously, and we are not really very good at looking for other methods of doing things. And again, if you look at the history of types, I think some of the work pretty much follows this idea, because if you're building the foundations of mathematics based on the theory of types, you care about completely different things than when you start using types to get better documentation in Julia language. So there's definitely been a lot of jumps in how types are used and what's the right method for building types. And what can we do if we don't have a good single definition of what is a type? We don't even know if there is one. I think there's a lot of room for creativity here. So this is the place where I think we can try to come up with better ways of dealing with types without really requiring that we all share the same definition. And I'll just have a couple of ideas here that might inspire someone. So the one idea is it's interesting to look at what we actually do with types. So when we are using types, let's have a look at not what the types really are, but what are we doing with them. And it could be the first statement here is kind of ambiguous. So it could be how do we use types in current programming languages. It could also be how do we actually talk about types. And the interesting challenge here, I think, is to construct interesting contexts in which types can appear. How many people here are familiar with the expression problem? Many? So the expression problem is this sort of programming puzzle where in object-oriented languages, we are really good at adding new classes. So we can, if we have some inheritance hierarchy, we know what's in, let's do animals. We have animals, and we have dogs and cats, and they both implement some animal operations. It's really easy to add a new animal. In functional style, when we define this as union, so animal is either dog or cat, it's really easy to add new operations, new functions that will do something with animals, but it's harder to add new kinds of animals. And that's really interesting context because it shows the limits of abstractions in a way. Like it tells you, well, in this one system, it's really easy to extend in this way. With this other notion of types, we can extend in another way. And there are programming languages that actually give you both of the sort of extensibility options. And I think this is one interesting context that sort of probes some properties about your types without actually requiring you to say what is a type. And I guess another interesting context would be if you're using types to provide some help in your editor. That's again something that doesn't really depend on what exactly you mean by a type, but you can sort of see what actually can you get. And it's again something that people from very different communities have been doing. Like there's editor tools for programming languages like Idris or Agda that falls to a very different camp than languages like Dart and TypeScript, where they also give you interesting programming tools. So this is sort of the idea of bridging the context there. Now the other approach is to treat types more as scientific entities, and there's a bit more on this idea in the essay if you want to have a look later. And in science, people sort of try to understand what is a scientific entity like electron. And one answer is, well, electron, you only know what it is when you can cause things with it. So when we know how to do something with electrons. And I think there's also interesting things to be said about what we can actually do with types without worrying about how that's specifically, like what's the theory behind it doesn't matter. When you can use types to build something and you see how it works, or you see that it works, that's an interesting result. So I'm going to wrap up, and it's just one more quote here from Paul Feyerabend that sort of I'm putting there to argue more that we can live without having one universal definition of types that everyone else has to agree with. And we can talk with people who have different idea about what types are. We just have to be a bit careful about it. And trying to always have this like precise definition of everything can hamper the growth of knowledge and deflect the course of investigation into narrow channels of things already understood. Thank you. Or eggs and tomatoes.